Good morning, everyone. And this week we will cover the electric flux, the Gauss's law, and the electric dipole. So let's first define what does the flux mean. The flux in general measures the vector field that goes through a defined surface. So this vector field, if we assume that we have a uniform vector field, then the normal component, as we will see, will be the ones that contribute into this flux. Why? Because the definition of the flux is the dot product between the vector field and the area vector. So in this case, if we know that the vector field is A, then the area vector basically is has the magnitude, which is the area of that surface, with the unit vector that is perpendicular on that surface. So if I take the dot product between the area vector and the vector field, I will end up with the magnitude of the first one times the magnitude of the second one times cosine theta, which means only the components that are perpendicular on that surface are the one that are going to contribute into this flux. So if we assume that we have this uniform vector field, as you can see, has the same magnitude everywhere with the same direction that is going through this surface defined by this closed contour, then the flux would be as simple as the magnitude times this area. Why? Because here, since it is perpendicular, then theta is 0, and that's why it will be as simple as the magnitude of the vector field times the magnitude of the area. Now let's take the electric field as our vector field. Then in this case, the electric flux would measure the amount of electric field that passing through this surface. However, as we said earlier, only the components that are perpendicular on the surface that are going to contribute into the flux. Why? So here, let's assume that we are dealing still with uniform electric field. And in this case, if this is my electric field that is uniform, this means that this electric field has magnitude, constant magnitude, and the same direction everywhere. In this case, I can decompose this electric field into two components. One of them is on the, if I take my coordinates this way, just to simplify it, one of them would be on the x-axis, which is parallel to that surface, and the second one would be perpendicular in the y-axis, which is perpendicular on that surface. And also the area vector A here, as you can see, has its magnitude A as this area of the surface, and the unit vector would be perpendicular, which is in this case n hat would be in the direction of j hat. So I can say that here A area vector equals to A magnitude times j hat. We said that the j hat in this case is our n hat. And here, this electric field I can decompose into two components. One of them is parallel, one of them is perpendicular. So if I am to take now the dot product, so this one is perpendicular j hat, and this one is E parallel magnitude I hat. So if I say here the flux equals to this E perpendicular j hat plus E parallel I hat dot this A j hat, I can see that the dot product between the j hat and the I hat would be 0 because they have theta of 90 degrees, and that's why cosine theta would be 0. In this case, I will end up only with the flux being E perpendicular A, because this is j hat, the dot product would be 1. So that's why I said only the perpendicular component on my surface is going to contribute to the flux. Now let's take this example. And here, if I am to, if I have this surface with an inner and outer radii of A and A capital lies in the xy plane as shown, we need to calculate the flux passing through this surface for the following electric field. So we have A, uniform electric field given by this expression, B, also uniform electric field given by this expression, and C, uniform electric field that's given by this expression. So let's first calculate the area vector here. My area vector here is the magnitude, which is, let's first put the greater circle, which is pi a squared minus the smaller minus pi a small letter, and then 3/4 of this shape. And then the normal unit vector is pointing in the positive z direction. So this now would be k hat. Rearranging this one is, let me take the pi outside, 3 pi over 4 a capital squared minus a small squared k hat. So this is my area vector. Now in order to calculate the flux for A, it will be uniform, so it will be right away E dot A, and in this case phi A would be minus ck hat dot 3 over 4 pi A squared minus A squared k hat, and in this case phi A would be k hat dot k hat is 1, so it will be minus 3 over 4 c pi a squared minus a squared. Remember, the flux is a scalar and it has a unit of Newton meter squared per coulomb. So this is for A. For B, notice that the unit vector here is I hat and my area vector is k hat, so the dot product would be 0. I have 0 flux going. Now this is, look at this minus c k hat. This tells me that the electric field is parallel to the z in the opposite direction, so it's coming this way. The B electric field is along the positive I hat. Now the last one has two components, one of them on the x and one of them on the z. If I take the dot product now between E and my area vector, notice that I have this one is going to contribute into a 0 because I hat dot k hat will give me 0. So only the second part of the electric field is going to contribute into my flux, electric flux, and the result would be minus 2 is gonna cancel with the 4, so minus the 3 over 2 c pi a squared minus a squared. Again, this is the flux for the electric field, for the third electric field, C. Now, what happens if this electric field is non-uniform? So far, we've seen what's going to happen if the electric field was uniform, but what happens if this electric field was non-uniform, which means that the electric field is not the same at everywhere and on that surface defined by this contour. In this case, we have to do an integration. So this one now is not uniform. In this case, I have to integrate now. Why? Because at every little area on this surface, I have different electric field. So I have to integrate in this case. Now I have to take an infinitesimal differential vector area and do the integration. However, we will simplify it and as we will see later on. Gauss's law says that the flux through a closed surface is proportional to the charge enclosed within that surface. So you can think of this closed surface in Gauss's law as a balloon, for example, that has the charges inside, and we're going to talk about the shape of this balloon or this closed surface. So we've seen that when we don't have a uniform electric field, in this case, we will have to integrate in order to find the flux through this area. This area defined by a closed contour, we call it an open surface. However, the balloon, for example, or the sphere, we call it a closed surface. So Gauss's law, as I said, it says that the flux through a closed surface equals to the charges enclosed divided by the permittivity of this medium. And for the case of a free space, it will be epsilon naught. So what does the flux equals to as well as the integration here, because we said that this is a general case. It will be now integration of the electric field over the differential surface vector of that closed surface. And that's why we have this little circle here. This little circle here tells me that my surface that I am doing the integration over is a closed surface. So in this case, once I see a closed and a surface differential vector element here, then in this case, I will be dealing with surfaces that are, for example, if it's a Gaussian surface, as we will see later on, if it's a sphere, then it will be the area of the sphere. Now, if the permittivity here is not a free space, it is an insulator that has a dielectric constant. In this case, we will substitute this epsilon naught with k epsilon naught, where k is the dielectric constant. We're going to come to the types of the surfaces. If we are to take a pointed charge, in this case, this pointed charge, the best, simplest surface to take as a closed surface would be a sphere. Then this sphere has a radius, as we can see here, radius r, which means that the electric field, if I am to take it as a sphere for this pointed charge, then at the same distance r, the electric field will be magnitude wise the same direction pointing away, which in this case agrees with the same direction of the area vector as we see here. So for example, if my area vector is a r hat and the electric field is also along the r hat. Then when I take the dot product here for this closed surface, since the electric field here is uniform, then and the direction, the unit vector is the same, then the dot product is going to result into the following, which is kq over r squared a. R hat dot r hat is 1, and now this dA. Now this electric field now can go outside, and that's why now it is outside. And now I'm doing the integration, closed surface integral for a differential surface is going to give me, for that sphere, is now going to give me A as the surface of the sphere. So now this is the integration of dA, and this is going to give me the surface of the sphere. Now the flux becomes the electric field that went outside times this surface of the sphere, and this is going to be q over epsilon naught. And this is what we have just said, that the flux the flux for a charge within a closed surface, that closed surface is a sphere, is indeed equals to the closed charge within this closed surface divided by epsilon naught if this region is a free space. Now, it depends on the value of this charge. This flux can be either positive or negative. If the charge inside this closed surface is positive, then it makes sense that the flux will be positive. Why? Because the electric field will be pointing outward. And in this case, I have the area vector is also pointing, as you can see, outward. So the angle theta would be 0. So in this case, it would be r hat dot r hat is going to give me 1. However, here, if the charge is negative, then as you can see, the electric field will not have an r hat, will have a minus r hat dot r hat. Now this is going to give me a negative flux. So the flux also has a positive or negative sign based on the type of the charge that is enclosed within this closed surface. Now remember, those closed surface that we have talked about so far are spherical closed surface, which are one of the common Gaussian surfaces and one of the easiest one. Once you're dealing with a pointed charge and due to the symmetry, then you can assume or you can deal with the electric field as a uniform electric field, which means it can go outside the integration. Now let's look at this question to evaluate our understanding to the Gauss's law. The question is asking, consider the two electric charges here. We call them electric dipole. We're only dealing now with the charges. Through which closed surfaces is the net electric flux equals to 0? So remember, what did we say about the closed surface? It doesn't have to, if you want to calculate the flux within a closed surface, it doesn't have to be a symmetrical surface. As long as it encloses the charges inside, then the flux would be this charge divided by the permittivity of the medium that the charges or the closed surface is enclosing. So let's evaluate now those surfaces. We have surface A, which is this one. We have surface B, which is this one. We have C, which is the largest one. And then we have D. Let's look at them one by one. For surface A, it does enclose, it's a closed surface. It looks a sphere. It does enclose a positive charge, which means it does have a positive flux. Then, in this case, it's not zero. So I will exclude A. So A is excluded. Let's evaluate B. B looks like a closed sphere, closed surface of a sphere shape. However, it does have a negative charge inside, and we know that the flux based on Gauss's law equals to the charge enclosed within that surface divided by the permittivity. So in this case, the flux for the charge for the surface B would be negative. So there is a charge and it will be a negative number. So B is not zero. Let's look at C. C does enclose two charges that are equal in magnitude opposite. I have the B and I have the A. So the netted charges inside this closed surface that is called C, although it doesn't have, a symmetrical shape. It's looks like a beam, but it's a closed surface. So in this case, what I worry about is the charges, the netted charges within that surface. Let's see how much are the netted charges within this closed surface that is called C. I have plus Q minus Q, so the net for C is zero. So the flux for the closed surface C is zero. Now let's look at the last one, which is D. I have D does not enclose any charge. Right away, the flux for D is zero, and in this case, it will be both surfaces C and D. Now, here, that's what we were talking about. It doesn't matter if you are interested in calculating the flux, only the flux. It doesn't matter what is the shape of this closed surface. It could be a balloon, it could be a bubble, it could be a sphere. What you what you worry about is the net charge within this closed surface. This is for the flux. So for me, this surface that looks like a sphere encloses this Q has the same flux as this surface. It doesn't matter the shape of the surface of this closed surface when it comes to calculating the net flux. What matters is the net charges enclosed closed within that closed sphere or surface. So here I have a sphere. It has a flux of q over epsilon naught, and the outer arbitrary closed surface also has the same q over epsilon naught. So the only difference is when it comes to calculating the electric field. For the arbitrary shaped closed surface, I cannot take the electric field outside the integration. Why? Because the electric field is not uniform all over the surface. However, for the spherical shape here, electric field would be uniform everywhere, right? Would be uniform everywhere because this sphere is a symmetrical closed surface and has the same and it is same distance everywhere, pointing in the same direction as the normal unit vector of the area vector. In this case, this symmetrical closed surface, which is a sphere for this point charge, will result into this electric field. The dot product will give me E dA, and now the E can go outside of the integration, and I will end up with E times A after integrating the surface. Well, I know that the result of the spherical shape doing the surface integral will result into the area of a sphere. So right away, the A, which is the closed surface integral of dA for the sphere, is 4 pi r squared right away. So one thing also to pay attention to in understanding the the flux, if we look at the flux for this symmetrical Gaussian closed surface, which basically we said that is going to result into, because of this point charge that is at the same distance, the electric field is uniform, is going to result into eventually EA, right? And we know that A for this sphere is 4 pi r squared, right? And we know that E for this pointed charge is kq over r squared. So it's going to result with the product of those two, which is 4 pi kq, right? Now, the interesting thing to notice here that the distance, the area is r squared, and the electric field divided by r squared, which means it will cancel, which means that the flux does not depend on the distance. This is a very important point. The flux does not depend on the distance. In other words, if you take the sphere, this Gaussian sphere here, it has the same flux as the bigger closed surface, has the same flux as another bigger closed surface. The flux does not depend on the distance of this Gaussian surface that you take. Now, let's look at this second example. So, in the previous slides, we were looking at the pointed charge, and that's why this pointed charge, it makes sense that we take the symmetrical Gaussian surface for it to be a sphere. But what would we take for a line of charge? A line of charge that has this electric field pointing in all directions. This is the line of charge. Electric field is pointing in all directions. In this case, the best Gaussian surface, symmetrical surface that we take for the line of charge would be a cylinder. The cylinder has a closed surface. As you can see, it is this shell, this face, and that face as well. However, when it comes to calculating the electric field, remember we said that the electric field on this shell would be uniform. Now, something to pay attention to, that the electric field, the the flux, the flux on this surface and this surface would be zero. Why zero? Because the electric field will be parallel in all direction. However, it would be parallel to this surface, and that which means that the dot product between this surface, which has a unit vector pointing, normal unit vector pointing in this direction, will result. So this is the n hat for the area vector. This is the n hat for the second surface. It's going to result into a dot product of zero. So the only surface that I need to include, I can include, is the surface of this shell. In this case, the flux would be, as I said, this is the general equation for the flux. Remember here, I have the charge density for this line of charge. So the total charges enclosed by this surface is this charge density times the length of this cylinder. Charge density times the length of the cylinder is the total charge enclosed by this Gaussian surface divided by the epsilon naught that we talked about. So in this case, if I am to derive the electric field relationship or expression for a line of a charge, in this case, we can use Gauss's law again. Electric field is uniform here, so electric field, the dot here is going to result into an integration of E dA, and then I can take the E outside. Then if I am to integrate only with respect to A, which is the area of this shell, would be the circumference here times the length L, and that's why we said that the area here for this is 2 pi r times L. So this is the area. Now, again, remember we said that the E went outside, then EA would be E times 2 pi r L equals to lambda L over epsilon naught. Now, if you want to calculate the electric field, then you move this, divide this one outside, you end up with E equals to lambda L over 2 pi R L epsilon naught, and then L cancels, right? And then you substitute 1 over 2 pi epsilon naught, this equals to 2K, right? Then this is the expression for the infinite line of a charge that we have seen earlier, or if you want to include the radial unit vector and the polar coordinates as rho hat, then the electric field would be 2k lambda over r rho hat. So this is how we can calculate the electric field. We can derive the electric field from Gauss's law, knowing the area of the Gaussian surface that we will be using.